Hello everyone, welcome to Course Seeded. Today we'll be studying about Q, BFS and DFS. So basically Q is another data type in C++. So for Q we can say that we have four functions in Q. Basically Q is something like this. So when you push, you'll be pushing from the last, you'll be pushing at the last index, and when you pop, you'll be popping at the first index. Basically you'll just remove the first element and last element will get added. So it's last in first out, LIFO. You just have to remember that it pushes at the end and pops at the front. So pushes at the back and pops at the front. That's what you have to remember for Q. Then you have a function named front for Q. Well, basically this gives you the first element in your Q. So if suppose you have these three elements, then this will give you front element and this will give you the back element. Now suppose if you have like an empty queue, mm, which basically nothing in there, an empty queue, so you won't be able to print anything from here. That's why queue is used. So basically queue is secure also. So next we have size. Obviously you know about the size function. So it just gives you the size of the queue. Basically if it's 5 or 3, basically this has size equals 3. So it's the length of your queue. So queue is done. So next we can move to BFS. Let me first implement this, then we can just move there. So here's the simple code, and then we can just run this. So basically what I'm doing is I'm first creating a queue of integer data type. Basically this is our data type queue, and then we have push I in that, basically from 0 to 9. And suppose if I do it equal to 10, then we'll have from 1 to 10, and we'll have just all the numbers from 1 to 10. Well, basically we have to check for not empty, and then we have to just see out front and then keep popping this. There is no other way. Well, basically there are few ways to check what all elements you have in queue, but this is how we do in competitive programming. Next we have like BFS. BFS is basically breadth first search. So basically it helps to find the shortest path, or sometimes it helps you to find levels and components too. So at first we'll be seeing the BFS, then we'll be implementing it. So basically how BFS works, so basically it starts at a root node. So suppose if you have a graph or a tree, you can say, well basically first let's study out graph. So basically if you have a graph, something like this. So if you have a graph like this and you want to find the shortest distance from 1 to 7, what is the best possible way to do so? Can anyone think about that? Well, first you can just travel all the sides from one, and then you can check which side is like the best, and it reaches from 1 to 7. That's one way. And second way, you can just like travel directly in one side and then return and then travel and then do it like this. So one is named as BFS and one is named as DFS. So here what I want to say is basically BFS starts at a root node, which is one you here you can say, and then it goes like it explores all the neighbors. So it will go to 3 and 4 simultaneously, or you can say one by one, but in a single like call. And then you'll have next it will go to 5 also. So basically it will travel 3 at once when it's called, and then from 5 it'll travel to 6 and 7 both. So basically this is an optimized approach. Basically it's used to find the shortest distance or shortest path for like this. So what we can do is basically we can iterate like this. First you obviously have to push the starting node. So basically there will be a starting node which you can mark as visited. So if suppose you have visited a node already, then you don't want to visit that again and again. So you'll have a visited vector, or you can say an array, in which you will be storing what all you have visited till now. And next you'll have a queue which is empty for now. A queue, then there you will be pushing the front node, basically the first node or the root node you can say, which is 1. And then what you can do is you can just mark all, you can just travel all, and then you can mark everything as visited in the visited. So let me first write the code and then explain it to you. Let me just directly implement it over here in the main function. So for now we are just doing for like unweighted graphs, and like we are not going for the weighted graphs. So we are just doing it normally. And also those are undirected graphs. Basically directed, where you have direction. So where you don't have any direction in this, you just have like you can travel both the side of node. Next what we can do is we can take a queue, and next we can do like push the first index. So for in our case we'll just have like the first index over here. So like let's first write the graph, and then basically let me just take the input as well for to and fro. So let me write it over here, then we can. So basically we are going from this to this. So we'll just be executing the path for that. First we'll be checking the distance, and then we'll be checking the path. So there's no problem in that. So first we have this queue, and then we can just push the fro button, or you can say from index. or from node you can say. Next we can do like, we can just introduce a new vector, and then if we want the distance or we want that whatever we need, so basically we can just like do, basically let me just write it over there and then you'll understand what I mean. Well, at many websites you will find that instead of writing fro, people write src, which is source node. So I also prefer that, but for your understanding I'm just writing fro and 2 over here, so that's not a problem. Basically u is our front, whatever we are taking. We majorly take u and q as our nodes, so we are taking first node as u, the front node which we have like the source node, or on which we are currently. Instead of writing and teacher, we can just directly write auto and then we can just take the nodes. So v is the second node on which we want to travel. U is the node which we have already traveled, or you can say which has already been taken. And v is the node which we'll be seeing in this. So basically, if v is not equal to u, then we'll be doing all this stuff. And if v is already equal to u, then we don't need much. So that's what I mean. Also, if you know, instead of just, we can just write over here as, well, if we are taking distance, then we don't need a visited array. But if we are doing like without distance, then we needed a visited array. So that's not a problem at all. Basically, up until now, we have been doing everything normally. So basically, whatever we have in u, will be just like printing that. So let's take the old example, which we had like 1 2 1 3 1 4 2 3 3 4. So basically, this was our example. In our case, the distance will be 1 for this one. So let's change it a bit. So basically, with 4, we'll be adding a 5 2. So over here, we'll be adding an additional, like, wait, let me write it over here. So basically, our new graph is like this: 4, and then 5, and then 3, and then 2, and then 1. Like this. And next, we're gonna have like this over here. And also, we'll have a 6 over here, which is not connected with this. Yeah, so basically, this looks perfect. So basically, we have like 6 nodes and 1 2 3 4 5 6 7 8, 8 edges. Well, basically I changed that from 4 5 to 3 5 first, because we will get that in ascending order. So that will be easier for us to like implement our logic over there. So we have like for auto v is to graph u, and then we'll have, if distance is not equal to -1, then we'll just travel the distance +1, and then we'll just add that in the queue. We'll add v into the queue, and this will happen for all v, so that's not a problem at all. Basically this is giving us the distance between v and u. So suppose if there are multiple, then we'll have like one distance from each place, but for path we'll have to do something different, so I'll be telling you that too. Like we are done with this, and then we can just like get our whatever we need distance. So for each, like, we'll get the distance between each node from the source node. So let's check that right over here. Also there's one more thing that I'll tell you what we can do, but for now let me just like write this over here. Yeah, so basically this is it. So we'll get all the distance from whatever we needed, and we can just say that if I is equal to like whatever we need, then like if it is I equals 2, then we can just like print that. Anyways, let's just run this, and then okay, so I, basically this is what we need, and I believe I'm doing everything right. Yeah, so basically, well, well, we are getting the answer, but we are getting it like something different than what we need. So basically nm. Okay, so this was 6 and this was 8. This was 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are 8 sample inputs. Okay, so so why are we getting it like this? We are getting time limit exceeded, right? Let me just check what I have done wrong and then I'll be back. So basically we are popping, so this is correct. The only thing that's wrong is basically it's this distance. And let me just comment out and then check where we are getting exactly time limit exceeded for each one. Basically I can comment this out and then check whether this for loop has been a problem or not. Okay, so this is successfully getting executed. Then we can choose the second for loop or while loop, and then we can check whether this is getting successfully executed or not. Otherwise, the problem lies in this while loop. Okay, so we are getting some runtime error. Okay, so I don't exactly see what the problem is. So this was basically like if it was -1, then we had to do this. Anyways, that's fine. Well, over here, like we just had to like do this. So now we are getting time limit exceeded. So for while loop is not equals to q dot empty. Uh, uh, uh. So okay, so this push, if I'm doing it outside, then it will always okay. Okay, so that push was supposed to be inside because I actually meant that inside only, but like I did that wrong. So anyways, the problem is fixed now. Well, basically that was giving us error because we was always getting like in that. So basically this is what we need. Okay, so we are not getting for I equals 6 for some reason. Mm, mm, mm. Distance between 1 and 6 is not visible to us. Okay, so because of this. Yeah, so this was supposed to be n plus 1, not n. And I believe our answer is not right for now. Yeah, so we are getting wrong answer. Let's see why this is happening. 1, 2 distance and then 1, 1, 1. And then this should be 3, right? Right. So where are we exactly going wrong? Okay, so this was also supposed to be n plus 1. Okay, so like we do some minor errors sometimes. So it's still wrong. So basically that means that there is some other problem over here. Let's see what the problem is. Okay, so for now I can't see any problem. So let's debug this. So nm from and to we have already written over here, 1 and 5. So we need a distance from like 1 to every place. So we have like 1 to 1 is 0, 1 to 2 is 1. So basically these all are at 1 distance, these 3, and this is at 0 distance, 1 itself. And then we have 5 at 2 distance, basically 1 4 5 or 1 3 5. Then we have 6 at the shortest distance as 1 4 5 6. Basically 3 are there, 3 edges are there, 1 2 and 3. So for this, what we are doing wrong is, we'll have to check that. Hmm. Okay, so for now I can't see any problem over it. Let me just rerun this. Okay, so we are still getting -1 as the answer. Uh, Let me just like see out this view over here again and again, so we'll get the answer what we are doing now. Let's see what we are doing now over here. Okay, so we traveled for 2 3 4 5, and then we never traveled for 6 for some reason. For some reason we are not traveling to 6. Mm, that's actually a problem. Well, let's see what we are doing now. Let me just quickly output the graph over here. Okay, so we have like 2 3 4 1 3 1 2 3 4. Okay, so we never had 6 over here. Well, wait, I definitely have done something now. Okay, so we had to do like I less than m over here. Okay, so if in last lecture if I did this n over here, then please rectify that. Because we have to like take the edges, not the nodes. So that was the mistake from my end. I'm so sorry for that. So in the last lecture, if I've done anything like this, then please do change that. So basically there should be m over here, not n. So now we are getting the correct answer. Okay, so for today let's keep it just this much. Afterwards we'll be doing the DFS, and then we'll be moving on to the next stuff. So for now, let's just keep it over here. Just keep it this much. Thank you everyone. Thank you for watching. Thank you so much.